Okay, hi everyone. So, lecture 9. Today we're going to come back to something which probably most of you have been thinking at the back of your mind. Surely we can do something better, which is the question of exploration exploitation. So far we've looked at really quite naive methods for exploration, where we've realized that there's an issue with our reinforcement learning algorithms, and one of the fundamental questions is how can a reinforcement learning agent balance exploration, kind of figuring out what's going on in its world, with exploitation, which means getting as much reward as possible along the way. And so far we've really tried very naive approaches like epsilon greedy. And this lecture we're really going to try and investigate specifically that aspect, that fundamental question of reinforcement learning. How can an agent which is down in the world trying to figure out how to get as much reward as possible whilst learning, how can it do as effectively as possible? And we're going to consider various different methods for that. And to do that, most of the lecture, we're going to start with a simplified version of the reinforcement learning problem, which we have seen on at least one occasion before. We're really going to spend some time to try and understand this simplified version, because it kind of boils down to the essence of exploration. And it's the multi-armed bandit, where you just get to kind of pick one action, get one reward, and that's the end of your episode. You kind of just have to explore and figure out what the best action is. Once we've understood that, in the remaining time, we'll spend most of our time here. In the remaining time, we'll touch on how to kind of bring back the full complexity of the whole reinforcement learning problem. But all of the ideas that we learn here apply. So if we don't have a lot of time here, you'll still get the essence of what's going on. So first of all, we'll bring back states. That's what we'll do with contextual bandits. We'll bring back states. And we'll say now, not only is there an action to choose, but there's also some state information. And that state information will inform what we do. One of the reasons to touch on contextual bandits is it's probably one of the most successful current application of machine learning. It's certainly one of the top ones, is using contextual bandits to decide how to do banner placement, banner ads for the internet. This has been used by many, many large companies to decide, you're in some state where you've got some user who's coming to this website, what should you show them? And then we'll finally come back to the full case of MDPs. Okay, so we'll start with a brief introduction to try and understand what's going on in this area. So every time we're decision making online, this same choice comes up again and again and again, which is, right now I can make a decision, I can take an action, but what should I do? Should I exploit, which essentially means to make the best decision given the information we have so far. So if you've got some information, maybe you figured out your value function, and according to that value function, you really believe that one action is the best. So exploitation means taking that best action, acting according to the max. Whereas exploration means doing something else. And there's a purpose to doing that something else, which is that we gather more information, which might lead us to make better decisions in the long run. So by gathering information, we believe that we might actually do better than taking what we currently believe is the best action. So often, the best long-term strategy might actually involve giving up reward in the short term. Like, we really believe right now that going left is going to give us more reward than going right. And yet we choose to go right. That's giving up reward. That's giving up reward we know we could get right now. And we're giving up that reward because we think we can get that reward back later. We think in the long term, it's better to explore, it's better to go through that right-hand door, because now we figure out, well, what's behind that door? Maybe there's a dragon there, but maybe there's a pot of gold there. And so sometimes we explore to find those pots of gold and work out what the better option is. And eventually we want to make sure that we make the best possible decisions. So here's a few examples. So, if you're going to a restaurant, you might want to explore by trying a new restaurant, or you might want to exploit by going to the one you know best. The online banner ads I mentioned already, but there you might want to explore by showing someone, a user, maybe you show them a different advert to what you've shown that kind of user before. But to exploit would be just to show the one you're most sure they're going to click on. You want to probably maximize click-through in these examples. If you're oil drilling, you might want to drill at the best known location, or you might want to explore by drilling at some new location. And if you're playing a game, you might exploit by playing the move you believe is best, or you might play an experimental move to explore. So in all kinds of different domains, why does this come up? It comes up because we're learning online. It's not just that someone gives us some batch of existing data, like in supervised learning. It's not there's a data set, and then we get to go over that data set as much as we want and make the one best decision. We're not in that setting. We're in the setting where we're gathering data as we go, and the actions we take affect the data that we see, and so sometimes it's worth taking different actions to get new data, to get parts of the data that we haven't seen so far. Okay. So that's the fundamental issue that's going on. We're going to focus on 3 different approaches to the exploration problem, the exploration-exploitation dilemma. These are not the only approaches, but I think there are 3 broad families that we should know about. And the first approach is what we've already seen, which is random exploration, which basically says, well, maybe a reasonable approach is just to sometimes, with some probability, pick a random action. An example of that would be epsilon greedy, or perhaps we might use a softmax distribution over our value function. These are ways to introduce randomness into the way that we pick actions. So we don't always just pick the greedy action, we throw in some dice roll, and if it comes up with a 6, then we choose something exploratory. In this lecture, we're also going to explore some more systematic approaches to exploration, which make more use of accumulating knowledge along the way. The first approach is known as optimism in the face of uncertainty. So this is like a fundamental principle that you should know about, and it basically says that if you're uncertain about the value of something, you should prefer to try that action. If you don't know, if there's one action that you're absolutely sure will give you 10, and there's another action which might give you anywhere between 5 and 20, which one would you take? Well, you should probably take the one which might give you 20, because in the long run, that means you'll be able to come back. If it turns out to be worth more than your safe option that gives you 10, then you should pick the option which has the greater potential, because it might turn out to be better. And then you can pick it again and again and again once you know that it's better. If it turns out to be worse, you've lost a little bit, but you can always go back to your preferred option. That's the idea of optimism in the face of uncertainty. So in order to do this, we need some way to measure our uncertainty on values, and we'll look at different ways to do that. There's a variety of different approaches, frequentist, Bayesian, and so forth. Finally, perhaps the most correct or theoretically careful approach to the exploration-exploitation dilemma, but the most computationally difficult, is to think about the information state space. So what this really means is to consider the agent's information itself as part of its state. So it's like, I'm in a state where I have tried left 3 times and I've tried right 1 time. That's a state now. We can say that's a state, and we can ask about how good is it to move into states where the agent has accumulated information. So if I might be in a state where I've never seen what's beyond that door over there, and that's a very different state to being in the same place, but knowing what's beyond that door over there. And so if we bring the information into part of our state description, then we can actually really understand how valuable is it to accumulate information. How valuable is it to find a new piece of knowledge about what's inside that door. Maybe it's a really good thing because it will help me to get more rewards later on, but maybe it doesn't actually have much effect because there isn't enough time to exploit those rewards, or all kinds of other issues. So this is the sort of correct but computationally very difficult, because our state space blows up to something massively more complicated and difficult than we had before. So those are the 3 approaches we're going to consider. I really, just before we continue, I wanted to touch on something which I consider quite a fundamental distinction in the way that we think about exploration. It's not talked about too much, but there's really 2 different spaces in which you can explore. We can explore in the state space or the action space. So this means that if you're in a state and you want to consider, should I go left or should I go right from this state, we know that maybe I've been in this state and I've taken the left action before. So now if I'm doing state action space exploration, that means I know something about the state actions I've considered. So if I come back to this state space, I might try going to the right the next time around. That's using knowledge about the state action space to help explore this whole state space more effectively. There's parts of the state space I've seen, parts of the state space I haven't seen. There's actions I've tried, there's actions I haven't tried. We use that knowledge to help us explore systematically and figure out the right rewards. But there's a different space in which we might choose to explore, which is the parameter space. So in the policy gradient lecture, we saw that it was possible not just to work with value functions, but to work directly with policies. And in that case, our policies have some parameters. This describes the behavior. This describes how my agent's going to operate for as it goes on in the world. Like I drop down my robot, it's going to behave according to whatever parameters make our IBO walk according to some way of walking around. And what you can do is you can try some parameters for a while and see how they do. Now, exploration, you could mean to say, well, let's try some different parameters, the ones we believe are best right now. Let's just try some different parameters, drop down a robot with a slightly different walk, see what happens, see how fast it moves, and go back and try it again. So I call this parameter exploration as opposed to state action exploration. And it has some advantages and disadvantages. So the main advantage is that you get some consistent exploration behavior. So you get to try something for a while. Like I change its policy, maybe I'm going to try out this strange walk, and I'm going to try this walk for a while and see how that walk does. Whereas if you contrast that to epsilon greedy, with epsilon greedy it's like you re-randomize at every single step. You pick another action randomly, and so you might end up just doing a random walk in your state action space, which might not get you anywhere. And so consistency in your exploration is sometimes helpful. We see this particularly in the robotics field. This has come up quite often. The main disadvantage of parameter exploration is it doesn't know about the state action space. So now if my random parameters that I've tried take me to some state I've been to before, I don't know that I've been to this state before, and I don't even recognize that maybe I've already tried this action over here and I already know something about that. We completely ignore that. It's like treated as a black box. And we're just looking at this black box. It's like doing global optimization in parameter space. So calling this exploration, really what we're doing here is more like global optimization of our parameters. We're trying to optimize in parameter space. Whereas here we're trying to really understand the state space, trying to understand the action space, and trying to systematically explore and figure out the parts of the state action space we haven't been to before. And of course there's compromises between. But on the whole, we're going to focus on this first section here for the rest of this lecture. Okay, any questions before I move on? Good. So we're going to start with the multi-arm bandit. So this is the multi-arm bandit. No octopuses required, but it's basically, we can think of this as a simplification of the MDP framework, where we just have a set of actions, A, and a reward function, R. So we've thrown away the state space, and we've thrown away the transition function, and we've really simplified things down now. So all that happens in this multi-arm bandit is, it's called the multi-arm bandit because of these machines, which are known as one-arm bandits in the US. And so you can imagine there's all these different machines, and you kind of get to choose one of these arms. And each of these different machines has a different payout, some probability that if you pull the arm, you'll win the game and get a payout. But they've all got different payouts, and maybe one of them's paying out 70% of the time, another one's paying out 75% of the time, and we don't know in advance which one's going to pay out the most money. So now, which one should we choose next? You might try this one and it works out quite well. Now you try this one, works out quite well, but should you go back to this one, or should you try this one again, or should you try something different? There's a whole strategy to your exploitation trade-off, where you want to ongoing make sure you're hitting the best machines as often as possible, but whilst exploring to figure out, to make sure you're actually finding and identifying the best machine. So, formally, we've got an action set, which tells us all the different arms of this thing. We've got a reward function, which is just the reward for some given action A. It tells us basically the probability of getting any different reward. So it's a distribution over rewards. So if I pull this arm, what's the distribution over the armor? The distribution over the reward that I'll get from this machine? What's the payout I'll get from it? So that's this thing. And there's a different distribution for each machine. And at every step, we just get to select one action. We get to pull one arm. And the environment generates a reward from the distribution. So we just sample from that distribution according to the arm that we pick. And the goal is to maximize the cumulative reward. So we just want to, over time, just keep accumulating more and more reward. So it's the simplest case. You can think of this as like a one-step MDP, where you kind of just have, there's one state and one step. So you basically pick your action, you get a reward, and that's the end of the episode. So there's no kind of, the only look ahead comes in that we're trying to understand the exploration-exploitation trade-off. So the look ahead comes in, you reach the end of your, you pull this arm, you see what happens, and now that affects your own information, that affects what you know about this environment. So you might want to then keep exploring or keep exploiting elsewhere. Okay, that's the multi-arm bandit. So are people clear about the setup, first of all? Should be fairly straightforward. So now we're just going to try and understand what it means to do well in this domain. So we've got this criterion where we want to maximize the cumulative reward, but we're just going to scale that thing, and we're going to basically flip it around to talk about opportunity loss known as regret rather than the amount of reward we've got, like how much worse have we done than the best we could possibly have done. And that's what we call regret. So to understand that, let's just work through a couple of definitions. So we're going to start off by defining the action value. So this is just like our familiar Q, but now we've thrown out states. There's no states anymore. So we've just got Q of A. So this is the expected reward that we'll get if we pull one of those arms. So this is the true payout of one of those machines, like how much it will really pay out if it's maybe 75% for machine 1 and 80% for machine 2. And the optimal value is the best that we could possibly do. If we knew which machine paid out the most, we would just always pick that machine again and again and again. So we would basically get the max of all our Q values because we'd always just choose the machine with the maximum payout. And that's the V star. That's the best we can do in this domain. We can just keep getting V star again and again and again. So the regret then is how much worse we do than V star. So V star is the best we could possibly get. We're just getting the best reward every single step we pick the best machine. But unfortunately, we might not know how to pick the best machine, so we incur some regret. We incur opportunity loss. And at every step, the opportunity loss we incur is the difference between the maximum we could have got at that step and the payout of the machine that we did pick. So this is the payout of the action we picked at time step t. So we picked something which pays out maybe 75%. We could have got 80%, so we incurred like a 5% regret for that step. We didn't pick the best machine. We picked something that was slightly suboptimal. So the regret then, the total regret, is just summing these opportunity losses over time. So we basically want to sum this up over time, and we want to see, well, what's the total regret that we're incurring if we just keep playing and keep playing forever. Okay? And so we're going to continue for t steps. We're going to play this game for t steps. And now we want to know if we play for t steps, how much opportunity loss do we incur? How much better could we have done? If we'd known the optimal value, if we'd known the optimal arm in advance, how much better could we have done? And so when we say we want to maximize cumulative reward, that's the same as trying to minimize total regret. Okay? And the reason it's useful to think about regret is just, we'll see shortly, it helps us understand how well an algorithm could possibly do. Like, independent of the scaling of the rewards, we can say things about how well our algorithm could do. We want to find algorithms which basically bring the regret at each step down towards 0. So just one more slide to understand like what's good and what's bad about regret, and then we'll move on to some pictures to help understand this a little bit better. So the count is just the number of times we've pulled an arm. So we're going to count the number of times we pull an arm. And we're going to consider this thing called the gap. So the gap is the difference in value between some action A and the optimal action. So it's basically the gap between the best machine I could have pulled and some suboptimal machine. So if I'm wondering, if I would just want to know what's the gap for machine 3, that's the difference in value between machine 3 and the best machine. So there's some gap. It's like the difference between 80% and 75% again. There's a gap there of 5%. And it turns out that we can think of regret as a function of all of these gaps and these counts. So if you just count how many times you use a machine, and you count also the gaps, like you look at the gap between how much you could have got and the actual payout for that machine, we see that the regret kind of breaks down in terms of those two things. So the regret, we basically saw that it was the sum of these differences. This is like your instantaneous opportunity loss, the difference between the optimal value, this is the best you could possibly have done, the payout for the best machine, and the payout for the machine you actually picked. So the amount that you lose at every step is the difference between the best you could have done at that step, the maximum that machine could have given you, and what you actually chose at that step. And then we just sum those things up, and we see that basically, we can just pull out the counts now. We can say, well, if we're just summing up how much we lost each time we picked this action, then that's the same as counting how many times we chose this action and multiplying it by how much we lost each time we did pick that action. So we just have to count how many times we picked this action, that's our count here, and multiply that by this gap, like how much worse that action was than usual. Yeah, question?
But we don't know the V star, right?
We don't know V star, yeah.
We don't know
V star. We don't know V star. Yes, we're going to come back to that. And so all of this is to say that we can just rewrite this regret, this thing we really care about optimizing, So we want to minimize our regret. We want to get as close as possible to optimal. But what we see is that the regret can be written in terms of these counts multiplied by these gaps. So what this tells us is that every time the gap is large, like if there's some action that you could take that's really, really terrible, like there's one of those machines is really horrible and it pays out 3% of the time, and there's a machine that pays out 90% of the time, well, the gap, which would be 87%, is very large, so you need to make sure that you pull that arm very few times. Whereas if there's another machine which has a small gap, you know, maybe it pays out 85% instead of 90%, and the gap is only 5% now. So now you want to, you know, you're okay with playing that one more and more. So what you really want to make sure is that you play the arms, you want to pick arms, the actions which are best as often as possible, and you want to pick the actions which are worst as infrequently as possible. It's intuitively obvious, but this is just saying it in math. And the problem is that these gaps aren't known. Like, we don't know these gaps. We can count how many times we pick an action, but we don't know the gaps because we don't know B star. Yeah, question?
The gaps obviously are different for each action, but they don't change over time, is that right?
This is for the stationary bandit where nothing changes over time.
Okay.
Yeah. There's extensions to this where it can change over
So
time.
do
Yeah.
we take expectation over the numbers of how many times we choose this action, or should we also take the expectation over the Q, as Q is like reward and sometimes is...
So Q is defined as the expected reward for
it's
that
already
action. That's the
expected.
definition of Q. So there's already an expectation in there. Yeah. Okay. So the real question here is what does this regret look like over time? And what we'll see is that for most naive algorithms, like if we're going to consider a few naive algorithms before we start to consider better ones, what happens is that the regret, so if this is like time over here, and this is the total regret that we've accumulated, you know, what happens if we use one of our familiar algorithms like epsilon greedy? Well, what's going to happen is that every single step in expectation, there's some probability that we'll pick the best action, but there's also some fixed probability that we'll pick completely at random. And if we pick completely at random, that's always going to incur some regret unless we just stumble accidentally upon the best action. And so if we keep picking randomly, we're just adding on regret. We're adding on a sort of constant amount of regret every step in expectation. So we're randomly picking amongst our actions. There's some probability that we'll pick each of those actions, and each of those actions will incur some opportunity loss. And so there's some total hits that we get for not picking the best thing, and that just keeps getting added on linearly every single step when we act epsilon greedily. When we act greedily, we also incur this linear regret, as we'll see, because we might lock onto the wrong action. And the question is, can we ever get sublinear regret? Can we get some regret which basically, we want regret which kind of essentially, we want something that starts to asymptote out. We want something which gets less and less regret. As we see more and more stuff, we want to basically do better and better and regret our choices less and less and less as we go on. And the question is, how can we achieve that? Is it possible to achieve sublinear total regret? And happily the answer is yes, and we'll see why. But let's just start by considering the myopic cases first of all. So let's start off with greedy algorithm. So if we were just to, let's start by considering our usual type of algorithms that basically do, you know, Monte Carlo learning, taking means. So if we assume that we estimate how good our machine is, so we're going to consider each of these arms now. We're going to consider each of the arms. We want to know how good is that arm. And the natural way to figure out how good that arm is just to estimate the action value by taking the mean of all the payouts you've seen so far. So if I've tried this arm and I got 10, and then I try this arm again and I got 8, now we think that our Q of A for that arm is 9. Okay? And so that's our way we're going to estimate the true expectations of rewards. So it's the normal way. Think of this as the normal way, just like Monte Carlo learning. This is the normal way that we estimate values. And so this is just another way to say that we're forming the empirical mean. This is just using our indicator. We've seen this notation before, so we're just saying the action value at time step t is just the average of all of the occasions. This is an indicator function that picks out all of the occasions on which we tried that particular arm, and we're collecting together so we're summing the payouts we got each time we picked that arm and forming the mean. This is just the mean then. Okay. So the greedy algorithm, what does it do? Well, it selects the action with the highest value. We just pick the action with the highest value. That's the natural thing to do. So we've estimated how good this action is. We've estimated how good this action is. If this one's higher, we just pick it. Okay? And the greedy algorithm doesn't explore at all. It just picks it, picks it, picks it, picks it. And the obvious problem is that it can lock onto a suboptimal action forever. Like I might try this action, and it looks good, and I thought this action was bad, so now I just keep applying this action forever. Or even I try this action, and I try it again, and I'm just a little bit unlucky, so I end up thinking its value is bad. And then I try this action once, and it looks better, and I just keep trying it and keep trying it and keep trying it. So you can lock onto suboptimal actions forever, and as a result, greedy has a linear total regret. But in expectation, you can do the wrong thing forever. If you can do the wrong thing forever, that means at every step, forever, you're going to incur the loss, the regret, for taking the wrong action. So you're going to get that gap again and again and again and again. Okay? So it should be clear that greedy has linear total regret, like you're making the same mistakes repeatedly forever with some probability. Okay? So what happens if we try and be clever? So the first idea to be clever is to use optimistic initialization. This is a really well-known algorithm, and actually, this is a really good idea. So I don't want to give the impression this is a bad idea. This works quite well in practice. There are lots of applications where it's quite hard to beat this. And the idea is just to initialize the values to their maximum possible. So we start off by assuming the best about all of our actions. So this is the simplest version we'll see of optimism in the face of uncertainty. We're not going to measure the uncertainty. We're just going to assume that everything is really good until proven otherwise. So we're going to assume that all of our actions pay out the maximum possible. So for this algorithm, we need to know the maximum possible. For many of the others that we'll see, we don't. So if we know the maximum possible, then what we do is we just initialize all our estimates to that maximum possible, and then we act greedily from that point onwards. Now, with optimistic initialization, you may want to not erase your optimism completely the first time you try that action, so you may prefer to take a non-stationary mean rather than the full mean. But again, so we start off assuming the best about things until proving otherwise, and then we still act greedily. And so this encourages exploration of things that we don't know about. But if you're unlucky about something a few times, you can still end up initializing something. So I start off thinking this action's the best possible, and then I try it and I'm unlucky, I try it again, I'm unlucky, and now I can still end up locking out this action forever because I might try this other action now, turns out to be better, and I never explore this one again. So you must have some kind of continued exploration to guarantee that you start doing better. Otherwise, again, you end up incurring the same regret every step. You can lock something out and just make the same mistakes again and again and again. So we want to find algorithms where we make fewer mistakes over time. That's really all this is saying. We want to find algorithms that make fewer mistakes as you get more experience. Yeah.
But how we update like the maximum reward we can get from that? Because I assume, okay, we have several arms and we assign maximum values for these arms, and then after every iteration, I need to somehow, if the value which I get is lower, I need to somehow update this, right? Update the arm.
Yeah. So, okay. So I should have spelt this out slightly more. So I think let me give what I consider the simplest implementation of this idea, which is to say that not only do we initialize the values to the maximum possible, but we also initialize the counts. So we say we believe that that this arm over here has. So let's take our octopus example again, where we know that we're going to get payout between 0% and 100%. So now we know that Rmax is 100%. You might get 100% payout on this particular machine. Whatever you put in, it might pay out 100%. Okay. So now we want to initialize everything to 100%, but we also want to say how confident are we that it's really at that value. So what you can do is you can say, let's imagine that I'd actually pulled that arm 100 times and set the value so far to 100%. So we might imagine that it's as if we played that arm 100 times and got 100% payout on every occasion. And now you continue from there, making your Monte Carlo updates, and you take an empirical mean, including those 100 updates that you've seen so far. So this is equivalent to using like a beta prior, which we'll see later. Okay, so that's the canonical version. So we assume that Rmax is known. We know the best possible thing. We initialize all our arms to the highest value. We assign some confidence and some crude way of estimating uncertainty that we know about that. So we start off by assuming that that we don't know the best thing. It's as if we've tried it a few times, but we haven't tried it forever. And now, as you start to receive more and more data, it will overwhelm your initial kind of prior on what you thought it was. So you just keep updating your means. So is that clear? You can start off by saying, yeah, it's just as if I've tried this arm 100 times and I saw the best possible payout 100 times. It's just as if I tried this thing 100 times and saw the best possible payout 100 times. And now if it really is terrible, you have to play it a lot of times to bring down the mean. And so it encourages you to keep exploring things until they're really proven to be suboptimal. And so, although I say it can lock out the optimal action forever, you have to be quite unlucky. So I think the more confidence you assign to your prior, the more unlucky you have to be to lock out the optimal action. So it's not a terrible idea to do this. Let's consider what we would say is the most naive algorithm that we've talked about. So I started this whole lecture by saying, look, what we've done before is naive, which is epsilon greedy. So let's consider epsilon greedy. So epsilon greedy, again, we just flip a coin every time step. We pick an action, we pull one of our arms with probability epsilon, we pull a completely random arm. Probability 1 minus epsilon, we pick the one we think is best so far. So now, what do we do? Well, we can be absolutely certain that we're going to incur some loss in expectation. We're going to keep making mistakes over time because we're still exploring randomly. So every time we explore randomly, we're very much likely to make some mistake and not pull the best arm. So we keep incurring regret and regret and regret. We keep making mistakes. And so this also has linear total regret. The same would be true for the softmax. I'm not going to go into the softmax here. But despite that, it turns out that if you just do something very simple, which is to decay your epsilon over time, which we've also talked about before, so you have some probability that you pick a random action, starts off at maybe 50%, and you just decay it slowly over time until it eventually reaches 0%. Now, it turns out that you can get sublinear regret. So, in particular, let's consider the following schedule. So, this is an impossible schedule. You can't do this in practice because it uses knowledge about V star, which we don't know. But let's say someone told us V star, and we could measure all of our gaps. Let's say we knew the size of all of our gaps, which we don't. If we knew the size of all our gaps, then what we could do is invent this schedule which says, okay, every step, all we care about is the size of the smallest gap. Like, what's the difference between the best action and the second best action? So if we know the difference between the best action and the second best action, we can use that difference to craft a schedule which looks something like this. Don't worry too much about the form of this. It's just saying, basically, whenever the gaps are very small, we want to explore those actions more often. If the gaps are very large, we want to explore them less often. That's intuitively clear.
Why is it second best on the average over the all where the gap is greater than 0?
Why don't we average over all of them?
Yes, why is it second best strategy, but not the average over the...
I think you could come up with many other schedules which would also satisfy this property, and averaging over them might well be able to do that. But this is like one simple schedule.
If you do the epsilon greedy strategy with the probability of epsilon, you choose the random strategy, which means that your delta would be, expectations of your delta will be average of suboptimal actions.
The expectations of D, or?
The delta.
This delta?
Yeah.
Okay. But we're not using the expectation of the gaps here. We're using, so one choice would be to use the expectation of the gaps, another choice is to use the min of the gaps. And to use that min of the gaps to just pick your schedule, that just determines the randomness that you use, and then you flip your coin with that according to that epsilon, choice of epsilon. So it's a valid choice. You could also use the expectation and come up with a different schedule. So just think of this as one choice for the schedule that depends on the exact individuals, individual gaps. And I think the main surprise here is that even this very naive approach, actually, it has logarithmic asymptotic total regret. So if we knew these gaps, we could, so what all this is saying is that actually epsilon greedy has the amazing property that if you decay epsilon according to the right properties, you essentially achieve the best results that you can get with bandits, give or take a constant factor and a term or two. And the only problem is that we don't know in advance what that schedule should be. But maybe it wasn't so naive at all, after all, what we were doing. Maybe epsilon greedy isn't quite as crazy. And I'll show some empirical results that kind of back that up. But what we really were after now is some kind of algorithm which achieves the same kind of sublinear regret as this idealized epsilon greedy, but without knowing the rewards in advance, without knowing B star and the gaps and all these things, so without advanced knowledge. So that's one way to understand these approaches. So if we just back up to the picture, really we're just after algorithms that have this kind of shape, and we've seen that decaying epsilon greedy has this shape. We make fewer and fewer mistakes over time as you decay your epsilon, but you need to know some special knowledge about the problem to be able to get the right schedule here, otherwise it ends up looking like this again. And so how do we make sure that we can achieve that without telling our agent things that it can't possibly know about the problem in advance? Okay? And so what I'm going to do is introduce a particular approach which achieves this nice property. It's very well known, one of the best known algorithms for, certainly best known algorithm for bandits, and very widely used in industry. But really I just want to give one more slide about the theory, which is just to say that it turns out that there's actually a lower bound on this regret. So in other words, there's something that says no algorithm can possibly do better than a certain lower bound. But there's some lower bound on how well we can do in terms of the regret. And what we want to do is basically push down our algorithms closer and closer towards this lower bound. And the lower bound is actually logarithmic in the number of steps. So what is this lower bound? Well, the performance of any algorithm, what does it depend on? Well, it depends on what makes a problem a bandit hard or easy. So consider how similar the best arm is to the other arms. If the distribution, so what makes a hard problem is basically a problem where you've got two arms which look similar, they've got kind of overlapping distributions, so you're not quite sure, it's not obvious which one is the best. So what's an easy problem? An easy problem is one where you've got one arm that's obviously good, one arm that's obviously bad. You just try this once and it gives you a good answer. You try this once, it gives you a bad answer. You're done. It's easy. Okay. A hard problem is something where you've actually still got one arm that's much better than the other, but there's a lot of noise on these things. So sometimes you take this one and it ends up looking really terrible. Sometimes you take this one and it ends up looking really good. And so now it's really hard to disambiguate them, and you're making a lot of mistakes, and it takes you a really long time to figure out that this arm is actually much better than this one. So the hardest problems have basically similar looking arms with different means. It's hard to tell the difference between them. And so formally, the way we understand that is by the gap between them, like what's the difference between this arm and this arm, and how similar their distributions are, which we can use the KL divergence. And so all this tells us, so this is one slide of theory, so the total regret is at least logarithmic in the number of steps. Okay, so the maximum, so this is the total regret that we're incurring over time. This is that plot we were looking at. And the regret that we incur is at least logarithmic in terms of the number of steps that we take, multiplied by this term, which is basically proportional to the gap. So this basically tells us that the more different the arms are, the more regret we'll incur, and inversely proportional to the difference in the distributions. So this is the term that tells us how hard the problem is. Hard problems have similar looking arms. That's the KL divergence between them, with different means. That's the gap here. Okay? So this is like the hardness of the problem. And so this is something which tells us about the problem. And this is something which is like fundamental to bandits and to exploration. There's this thing which is logarithmic in the number of time steps. So we want to find algorithms which have a regret that's logarithmic rather than linear. Okay. So let's get back to principles and then come back to algorithms again. So this is the main principle that we're going to use for this next section, which is the optimism in the face of uncertainty principle. So imagine that there are three different arms. So here's three different arms. There's the blue arm, the red arm, and the green arm. Okay? And what we're showing here is a distribution over the actual Q values there. So this is, so imagine this is like our belief. So right now, I've tried a few actions. Maybe I've tried this green one a lot of times, so I've got quite a good idea of what the mean of this green action is. I'm pretty sure that it's around in this range somewhere. And this x-axis tells us how good we think it is. So the further along this axis means this is basically the value that we expect to get from our payouts. And this one has a width something like this. We've tried it quite a few times. So this is our distribution over Q. We believe that the mean of this arm is somewhere around, I can't read these, 2 point something. Whereas this blue one, maybe we've only tried a couple of times and we're really not sure what the mean is. We think it's somewhere around here, but it could essentially be anything. And the red one's somewhere in between. And the question is, which arm should we pick next? So the optimism in the face of uncertainty principle says, don't take the one you currently believe is best. That's the green one. Take the one which has the most potential to be best. And in that case, this would be the blue arm. And the blue arm has the most potential to actually have a mean which is somewhere over here. If we look at it, the tail of this distribution has quite a lot of mass that says, hang on a minute, there's quite a good chance that this blue arm might turn out to have 3 or 4 or even more, a mean of 3 or 4, a really high payout. So we should really try that blue one and narrow down this distribution. And the idea of the optimism principle is that as you try it, you start to narrow down this distribution. So maybe you play this arm, you think that this one's got the biggest tail, you play it, and now maybe it turns out it's really a bad action. So now the distribution will be narrowed around something that's shifted a bit over this way, and the tail will be brought in, and now maybe you don't play that one again. So now maybe you try the red arm. Maybe that one also turns out to be bad. That will shrink the tail back in again. You'll end up with a distribution something like that. And now you'll play the green arm. That will narrow it down again. And as you narrow these things down, you start to get more and more sure about where the best action really is, until you're actually just picking the one that's actually got the maximum mean. So it's a way to really just keep doing things, pushing down your uncertainty, but at the same time trying the thing which has the most potential to do well. So this is the optimism in the face of uncertainty principle. And so the difficulty is that so far we've only talked about ways to estimate the mean. We haven't talked about ways to estimate this uncertainty here when we've talked about estimating Q values. So we're going to talk about 2 different approaches now to solving this approach, one of which is frequentist, in which we assume nothing about the distribution, and the second approach is Bayesian, where we assume that someone gives us a prior probability distribution over our Q values. Okay, and the general idea we're going to use is something called upper confidence bounds. So the idea is to say, let's come up with an upper confidence for each action value. So we're basically going to say, I'm not only going to estimate the mean, like the payout I've seen so far. Maybe I've seen 80% payout for this particular arm so far. And I'm going to estimate some upper confidence on what I think that could be. Like this is like, think of this as the tail of that distribution we just looked at. So we're estimating, for each of these things, we're not only going to estimate its Q value and estimate its mean, we're also going to estimate some kind of addition. We're going to add on like some bonus to this thing, which characterizes how big this tail is of that distribution. We're going to pick the thing with the highest bonus, the highest sum of Q plus something which tells us about this tail. So we're going to end up picking the thing which, where we sum those 2 things together, it gives us the maximum value. So we're going to estimate this upper confidence U. So we can think of this as a high probability upper confidence on what that value could be. So think of this as something like a 95% confidence interval about where the mean could actually be. So we're going to say, maybe I'm 95% confident that this one is going to be within this range here. And so that gives us our point that we use. That's our U value here now. And compared to this one, we might say a 95% confidence interval is here. We're going to use that as our U value. So think of them as like confidence intervals, high probability confidence intervals on what our Q value could possibly be. We're going to pick the thing with the highest upper confidence value. So that basically means we're going to pick the one where the true action value, Q, A, we want to pick something where we're really confident that the true value is less than our upper confidence bound. So we're going to pick an upper confidence bound, this 95% confidence range, and pick the thing with the highest upper confidence value. And now this depends on how many times we've tried it. So the fewer times we actually try a particular action, the larger our upper confidence will be. And the more times we try a particular action, the smaller the upper confidence will be. So we add on less and less of a bonus to things that we've tried more. We become more and more confident about what the mean is. Eventually, we end up just using the means. When you try something enough, if you tried an action infinitely many times, you just select that action based on how good it really is. Because now we really know for sure what the mean of that action is. Up until that point, we use some upper confidence on how good we think it might end up being. Use the 95% interval. And so the algorithm is really simple. We call this UCB. We select the action that maximizes the upper confidence bound. So instead of maximizing over Q, or instead of adding on some random thing, we pick the action that maximizes Q plus this upper confidence value, U. Okay. Is that clear? Some glazed looks, some people clear. Okay, any questions? Help deglaze people. Okay.
So the UT goes to 0 as you try as many?
Yes. The U values go to 0 as you try more and more actions. So eventually, the U values, it's just like shrinking this tail here. The U value is characterizing the size of this tail. So if you try this red guy more and more, it's going to shrink down. It's going to shrink. So think of, you start off with some confidence interval that looks like this. This is your U value. The U value is the difference between the mean and this guy. And as you try it more and more, this is going to shrink down. You become more and more confident of where your Q value actually is, until eventually that U value shrinks to 0 and you just use the mean. Okay. So you really want to just keep picking things according to this upper confidence value, and that helps you very systematically look around your action space and figure out systematically which of those actions is giving you the best results.
Are you making some assumption about symmetry of the distribution here as well?
Okay, great question. Am I making any assumptions about the symmetry of the distribution? So for the approach I'm about to show, we make no assumptions about the distribution, and then we'll talk about ways to make use of assumptions about the distribution. Okay, so this is the distribution-free version. We're just going to use, this is a fundamental inequality from probability theory, from statistics. And so let's just forget reinforcement learning for a second and understand what this is saying. This is called Huffling's inequality, and it's just a fundamental inequality that basically tells us that if you have some random variables, so if you're basically sampling these random variables between 0 and 1, so we've got these x values, and you keep sampling those x values again and again and again, and we take an empirical mean of all of our samples that we've seen so far. So you just keep seeing this data, you keep seeing this data, you take a mean of that data, then what's the probability that the sample mean is actually less? So what we want to know is, if we take our sample mean, that is the x bar, and we consider some, so what's the difference, what's the probability that we're wrong by an amount of u in our estimate of the empirical mean? So what's the probability that the difference between the empirical mean and the true mean is greater than u? Right? What's the probability that we're actually making a mistake in our estimation of this empirical mean by at least u? Okay? You've just seen a bunch of coin tosses, and what's the chance that the mean of your coin tosses is actually different from the real bias of your coin by more than u? And it turns out that you can bound this thing by this arbitrary seeming exponential value, and this is true for any distribution. Doesn't matter what the distribution is, doesn't matter if it's symmetric, doesn't matter anything about it. This is always true. In fact, it's maybe a little bit weak because of that. It's not making a lot of assumptions, and therefore it's perhaps quite a weak inequality. Yeah?
So in the case of the bandit though, so this requires that you have like bounded rewards.
This requires that you have bounded rewards. So if you don't have rewards in the range 0 to 1, we just scale them to 0 to 1. Or there's another version of Huffling's inequality that uses arbitrary range values. But the version I'm going to use is simpler, and so the easiest way to do this is you just scale your rewards back into 0, 1, and exactly all this theory applies. But that means you know the bound, you know some range on your, our max and our min.
As in, like, if your rewards are like normally distributed, so there is no like So there's no like maximum value that you can get. And you
Yeah,
can't
this assumes, for this result, it assumes that you've got a bounded distribution. So there is at least one assumption. It's true for any bounded distribution. Thank you. So we will apply Huffling's inequality to the bandit case. So all we're doing here is we're applying exactly the same inequality here. And now we see this is basically saying what's the probability that I'm wrong in my estimate of these Q values by more than my U value. And what we're going to do is we're going to use this to solve for the U value, to set this upper confidence value to the appropriate amount. So we want to know where should I place my upper confidence thing to guarantee that this probability is, say, within the 95% interval. So this gives us a way to compute like these 95% confidence intervals. Because we know that the probability that I'm making a mistake of more than this U value is bounded by this value. So if we plug in this thing to be 5%, then we'll solve for our upper confidence value in a very general way. So that's what we're going to do now. So we're going to pick a probability. So this is like picking our 95% interval. We're going to pick for that p-value. We're going to solve for our u. And so all we do is we just set this thing, set the right-hand side of our Huffling inequality. This is the probability that we make that mistake. We set that to some value, like our 5% interval. And we solve for u. So to solve for this, we just take logs, which gives us this thing. We divide through by minus 2n, and we take a square root. This is squared. And that gives us this upper confidence value. So it seems rather arbitrary, but what's nice about it is we don't need to know anything about the gaps, we don't need to know anything about the rewards except that they're bounded, and now we have a way to pick actions. We just maximize, we add on this term here, and this term has all the properties we wanted. You can see in the denominator that the count here is in the denominator. That means that as we pick things more and more and more, this bonus term is going to get pushed down towards 0. And for actions that we haven't tried very often, they're going to have a very large bonus term. So the less we've tried something, the more uncertain we are, and the more we add on to this bonus. Gives our interval. And now what we do is we pick in something like a schedule, where what we actually want to do is to make sure that we actually guarantee that we pick the optimal action as we continue. We want to really get these asymptotic regret things to be logarithmic. So the second thing we do is we add a schedule to our p-value. So we don't fix it to like 95%. Instead, what we do is we slowly increase this thing over time to be more and more confident that we've included the true q value in our interval. So what we want to make sure is that we are guaranteeing that we select the optimal action as t goes to infinity. Okay, so here's the algorithm. And if you like, if the theory was kind of uninteresting to you, you can just use this algorithm. You can just view this as an empirical fact. Here's an algorithm I can use, and this will work. And it works very well in practice. And so this is the Ucp1 algorithm. There are many extensions, hence the one. It's been followed up in all kinds of different approaches. But the basic idea is that every step, you estimate your q values by taking this Monte Carlo estimate in the usual way. So you just take the empirical mean of everything you've seen so far. And then you add this bonus term on that only depends on the number of time steps, the number of total pulls of all of your arms, and the number of times you've pulled this arm. That's all it depends on. And you add on this bonus that depends on those two things, and you pick the action with the highest total value. And this thing actually then achieves this logarithmic asymptotic total regret. So it looks a lot like the lower bound, except we've lost one of the two terms. We don't have the KL term in there. But we do have the logarithmic. It's logarithmic in terms of the number of steps. It takes account of the action gap, but it doesn't know about the distribution, so it doesn't have this KL term in there.
Will be brackets inside argmax?
So this is saying we want to take the argmax of all of this.
Right. What should we do with the bracket?
Depends on your operator precedence. Right. Okay. So it's an algorithm. How does it do in practice? So this is comparing UCB and epsilon greedy on a 10-armed bandit. And this 10-armed bandit has particular characteristic on the arms, and this is looking at different types of distribution. So this is like 10 machines which have parameters where one of them pays out 90% of the time and all the others pay out 60% of the time. And here we've got one of them pays out 90% of the time, 3 of them pay out 80% of the time, 3 of them pay out 70% of the time, and so forth. So it's like different types of distribution, and the question is, how well do these algorithms do? And so what this is comparing is these UCB algorithms with epsilon greedy with a decaying schedule, but instead of trying to know the schedule in advance, it's like trying to guess what the right schedule is and just decaying according to some guessed schedule instead. And so the surprise is, again, that epsilon greedy does well. Okay, so epsilon greedy, if you tune it just right, actually does really well. The difficulty is that if you get it wrong, it's a disaster. So whereas UCB, without any knowledge about the problem, actually systematically performs really quite well in these problems. So it might be difficult to pick out, but yeah, in each case the UCB algorithm is doing really very well. And what we're looking at is the total regret here on the right-hand side. This is the total regret over time, and you can see that if you use the wrong epsilon value, things just blow up. But the UCB algorithms do really quite well. And on the left-hand side, we're seeing, I think, how many times you pick the best action. And so what you see is that eventually all of these algorithms start to converge on picking the best action 100% of the time, which you don't get with a naive epsilon greedy or some other naive algorithms. Okay, so this is the Bandit algorithm. So these ideas can be continued. So this Huffling inequality you can think of as an example of a general kind of procedure for generating algorithms. People have subsequently plugged in many other inequalities, generated tighter bounds, different bounds for different types of distributions, different knowledge you can plug in. It goes on and on and on. So there's a whole program of research. It's been one of the most explored areas in machine learning in the last few years. So I mentioned earlier that I was going to talk about two approaches, a frequentist approach, which we've seen, that makes minimal assumptions about the distribution, but we can also consider a Bayesian approach to the Bandit idea, to the upper confidence idea. And what we do now is we can exploit prior knowledge about the rewards. So what if someone gives us a prior distribution over what our Q values are? Can we make use of that? Like if we know that we've got some prior distribution where I'm pretty sure that this action is better than this one, can we make use of that information? And so the Bayesian Bandit does that by starting off with some distribution over the action value function that's parameterized. So we have a parameterized distribution, so we have some distribution over our Q values, parameterized by a parameter vector W. And what the Bayesian approach does is it starts to, with experience, update these W's. So an example of the W's would be the means and the variances of each of our arms, the Q values for each of our arms. So an example would be, let's parameterize our uncertainty over Q by estimating the mean of Q and the variance of Q for this action, and for this action, and for this action. And so you'd have 6 parameters then describing everything we believe about those Q values. We've got the means, which is what we normally track, but also the variances. And so the Bayesian approach literally computes a posterior distribution over what these things look like after the data that we've seen so far. And then it uses that information to make our decisions. So the idea of the Bayesian approach is we compute a posterior distribution over our parameters, the means and the variances, or whatever those parameters are, given the pools that we've seen so far, and then use that posterior to guide exploration. And so there's a couple of ways we can do that. I'll first of all talk about upper confidence bounds, but also probability matching. And the main point of this whole approach is that if we have prior knowledge that's accurate, like if someone actually gave us prior knowledge that was useful, then this can do a lot better. Like if we know that these things are Gaussian, then we can do much better. If our prior knowledge is wrong, you're probably better off using the UCB approach we just saw, which is robust to different distribution assumptions. Okay, so how can we use this Bayesian idea to compute upper confidence bounds? Well, first of all, we compute our posterior. We update our parameters given the data that we've seen so far. So we update both the means in the normal way, but also the our variance parameter. And then what we do is, and we can do that basically by using Bayes' law. So the probability of the Q value is conditioned on everything we've seen so far. It's just, we multiply, this is just Bayes' law. And then what we do is we just want to compute, again, something which characterizes the tail of this distribution. We want to get the equivalent of our 95% confidence band again. So what we do is we just add on, the U value that we add on now is just some multiplier, some number of standard deviations of our posterior distribution. So we look at the width. Now we're not sure what this mean really looks like. We characterize the width by some variance, and then we say, okay, I'm going to take the mean plus 3 standard deviations, and I'm going to use that value. And I'm going to compare that to the red guy, where I'm going to take the mean plus 3 standard deviations. And then we see that the blue guy has a higher combined value than the red guy, so we pick that one. That's the idea of the Bayesian approach to upper confidence bounds. So it's really the same idea as the UCB algorithm that we just saw, but using prior information and updating our posteriors more explicitly. We're explicitly estimating this distribution, whereas before we weren't even tracking the distribution at all, and we were just using a fact about distributions in general to give us our upper confidence bound. Okay. There's a second way to make use of our probability distribution. So if we've computed all of these posterior distributions over our action values, so we've got the blue guy and the red guy and the green guy, there's another way to make use of this information. And this is also true for any Bayesian method. And the idea is to do something called probability matching. So this is instead of the upper confidence bound idea, you can do something called probability matching. And so the idea is to select an action according to the probability that that action is actually the best one. So if I've got 2 actions and I kind of can compute that, you know, according to my beliefs so far, maybe there's a 30% chance that this action's the best, and there's a 70% chance that this action's the best. So then I just sample those actions in proportion to my belief that they're the best one. So then I actually pick this one 70% of the time and this one 30% of the time. So that's the idea of probability matching. It's a heuristic. It's a heuristic that guides us to picking the action most, which has the chance of being the best, the highest chance of being the best. So in other words, our policy, the way in which we actually pick actions, is just the probability that our Q value for that action is actually the best Q value. So we want to pick actions in proportion to the probability they're actually the best one. And so what's nice about probability matching is it automatically does this optimism in the face of uncertainty idea. In other words, if we've got some uncertainty over our Q values, and then we kind of just, if we just probability match, we automatically pick things which are which have higher uncertainty. Like the more uncertainty there is in something, the more chance that thing actually could turn out to be the max. In other words, if we look at these distributions again, you know, what's the probability that blue is actually going to end up being the max? It's fairly high. There's a good chance that blue will actually end up being the max because it has this big tail there. Whereas there's a relatively small chance that if you had something, you know, over here with a tight distribution, there's a very small chance that this thing could end up being the max, and so we would never pick it. So we pick things in proportion to the probability that they could be the max, and that encourages us again to be optimistic in the face of uncertainty. Okay, so how do we do this in practice? Well, there's a very simple way to do this, and it's called Thompson sampling. And this is actually the oldest algorithm for bandits. It comes from like the 1930s, before bandits were even really kind of formally studied. And yet it's turned out, surprisingly, to have come around full circle to the point where this now is known to be actually asymptotically optimal. So this is the first algorithm we've seen that actually achieves that lower bound that we've seen for a particular class of algorithms, like this, at least for Bernoulli Bandits, which is a special case. So this idea actually works optimally well in terms of the expected, the total regret which you incur. So the idea is just to do probability matching in a sample-based way. So every step, you just sample your posterior. So you pick a sample from your posterior. So what you do is if these were your distributions, you just sample from them. You randomly sample from your own distribution for this guy. You say, okay, well, let's just randomly sample from this Gaussian. Maybe I think that the value is now here. I randomly sample from this guy. Maybe I end up thinking, well, it's here. And then I randomly sample from this guy, and I end up picking something which is, say, here. And now all I do is I just look at my samples. And according to the samples, I've got one here, one here, one here. I just pick the one which was best out of my samples, and I go with that action. So it's almost like the simplest way you could think of to use this information, and yet it's actually asymptotically optimal. It achieves that lower bound that we saw with the Bernoulli Bandit case. And it also has this nice property that automatically shapes itself. It's not like the previous approach where we had to pick how many standard deviations to consider. We had this free parameter, how many standard deviations should I use? With probability matching and Thompson sampling, you don't have that parameter. It just comes out in the wash. Everything just works. It's sort of parameter free. I mean, implicitly there's parameters in the prior distribution that you use, but once you've got your prior, it's parameter free. Okay, so that's Thompson sampling. You basically, and this is a very general idea. So you can think of this in general. You can have any distribution. You could have some shared parameters characterizing the distribution of your robot, having some action value function, and you just sample from the parameters characterizing your distribution. And once you've got your samples, you just pick the action which achieves the best result in those samples, according to those samples. Right. Let's just see how we do. Okay. Let me just pause there, take questions, and then we'll move on to the next section. Questions? Yes?
How does the situation change if you know you have only a certain number of experiments that you can run?
Okay, great question. How does the situation change if you've got a limited budget? So it really changes the bandit problem to impose a budget. Actually, some of these algorithms do not do the right thing. They assume that you have an infinite budget. You keep going and going and going. The next family of algorithms we're going to look at deals with that correctly. So I would say, yeah, just wait maybe, and we'll see something. Any other questions? Yeah.
Is this Thompson sampling method, in general, good? So it's optimal for Bernoulli Bandits, but is it good for other algorithms?
Yeah, there's a lot of experimental evidence recently showing that it actually, across a lot of different bandit types, it performs at least as well as UCB-like methods. I think there's a question over Bayesian bandits in general. So Bayesian bandits are only as good as the prior knowledge you put into them. So if your prior knowledge is, if you have some magical source of prior knowledge, great. If you don't have a magical source of prior knowledge, it's not so clear that you want to take a Bayesian approach, at least in terms of the prior you put in. I mean, what's nice about this is, okay, this lower bound starts off by assuming like a flat prior. So if you just use a flat prior for the Bernoulli Bandit, then you can make progress. So yeah, I mean, I think it's an encouraging approach, and it's being quite widely explored at the moment. There are some issues with Thompson sampling in the full MDP case, that it doesn't necessarily deal with sequential information very well, right? Because you're randomly picking at each time step, you lose the kind of consistency of exploration again. Okay, let's move on. So far we've seen two of our three classes of approach. We've seen randomized exploration algorithms that kind of randomly, like epsilon greedy, randomly explore. We've seen upper confidence algorithms, optimism in the face of uncertainty, and now we're going to consider our third class, which is state space, information state space algorithms. To understand information states, let's start by talking about the value of information. So let's think about exploration. Why is exploration useful? Exploration is useful because it actually gains information. Like if you weren't gaining information, if you just tried some action, but then you weren't told how much reward you got from taking that action, there would be no point to explore. You wouldn't be able to learn from it. So exploration is useful because we gain information. So if we can quantify the value of that information we've got, we can trade it off perfectly. Like if we know that, if I've got two rooms, one of them I know what's inside that room, another room I don't know what's inside that room, if I can quantify how much long-term reward I would gain by exploring the unknown room, how much is that worth to me in terms of units of future reward? If I can quantify that, I can make the perfect decision about whether to go into that room or not. So the value of information is trying to quantify the value in terms of units of reward of actually taking an exploratory action. So we can think of this as, how much, if I'm an agent and I'm making decisions, how much am I prepared to pay to take some action that I currently believe is suboptimal? So I know that I can get, £100 by pulling this lever, but I'm not sure how much I'll gain by pressing this other lever over here. I think right now it's worth about £70 to me. So can I quantify how much it's worth to me to pull this lever in terms of my future payout? And the value of information depends on all kinds of things, one of which is the budget, one of which is, how many more times will I be able to play this thing? If I'm only able to play this thing, 3 more times, it's probably the value of that information is less, because I'd rather just take the £100 because, I'm not, even if I figure this thing out, I'm only going to be able to play it a couple more times. Whereas if I know that the budget is going to continue for the next 1,000 steps, then I'm more tempted to try. The value of information is greater. So we can think of this as the long-term reward after getting information, take away the immediate reward. So the difference between how much we gain by having this piece of information compared to just the immediate gain of getting the £70 or whatever from taking this action. So information gain is higher in uncertain situations. So if you know everything about a situation, there's nothing to be gained by acquiring more information. We already know exactly the right thing to do there. So what we want to do is to explore uncertain situations more, but we want to kind of do this optimally. We really want to figure out what's the perfect way to balance exploration and exploitation. Everything we've seen so far, in some sense, is a heuristic. Upper confidence bounds, it's a heuristic. Thompson sampling, it's a heuristic. All these things are heuristics that, in the more complicated cases, those heuristics start to break down, particularly when we start to look at full MDPs. So what's the real best way to trade off exploration and exploitation? So the way we can do this is to think of an information state space. So we're going to now transform our bandit problem back into an MDP, into a sequential decision-making problem. And the way we're going to do this is we're going to think about an information state, this S tilde thing here. It's going to be, that's what we know so far. This is a summary of all the information we've accumulated so far. So this summary we can think of as like, I've pulled this lever 3 times and this lever 5 times. That would be an example of an information state. And now, what we're going to do is each time we actually take an action, it's going to transition us. We're going to have like an MDP with a transition probability that transitions us into some new information state. Like I know that if I was in a state where I've pulled this lever 3 times and this lever 5 times, and I pull this lever again, then I know I'll be in an information state where I've pulled this lever 3 times and this lever 6 times. That's my transitions. I've got an MDP now where I'm transitioning from information state to information state. And so we can define an MDP over information states now. So we've augmented our original problem, our bandit problem, into an augmented information state space. We've got this M tilde, that's our overall MDP. And now we've got this information state space. We've got our normal action space, these are the levers, the arms of my bandit. We've got our transition matrix, this is the way that we transition from information state to information state. We've got my normal reward function. We've augmented our action space and our reward space, our original bandit problem, which was A and R. We've augmented it to make an MDP out of this thing that takes us from information state to information state as we traverse this bandit, as we try different things. This is a very large MDP. This tells us about all the different possible information states we could be in as we start to explore this bandit. So let's consider the simplest case. Let's consider Bernoulli Bandits. So a Bernoulli Bandit is basically like a coin flip bandit, where the reward function is just you flip a coin, and with some probability mu A, so for action A, like the left lever, there's some bias to that coin that tells me if I'm either going to get a reward of 1 or 0. So with probability mu A, I'll get a reward of 1. So just like a coin flip with some bias, or we can think of this as our machines with the octopus again. This is the payout of those machines. probability that this machine will actually pay out when I pull that off. And an example of this would be like a pharmaceutical drug company, and you want to do a test, and you want to try someone on this drug, and with probability mu a they get better, and with probability 1 minus mu a they don't get better, and that's your Bernoulli Bandit problem, and you want to find the medication, the drug that's got the most chance of succeeding. And so what's the information state here? Well, the information state is the counts. That's one example of the information state. It's the counts. How many times have I pulled this arm and it's failed, and how many times have I pulled this arm and it's succeeded? So how many times did I try this drug on someone and they got better, and how many times did they not get better? And if I can keep those statistics summarize everything I've seen so far. A sufficient statistic of that's given all of the tools that we've made in this bandit problem. So just to make that concrete, you probably can't see this at all. It's very small and blurry, so I'll read it to you, or at least explain it. So this is our drug example. We've got two different drugs that we're considering. This is the American sense of drug. We're not talking about heroin or something. Well, you can imagine it that way if you like. I'm going to think of it as a pharmaceutical drug. And there's two different arms you can pull. That's the two different drugs. So I've got some patients, and I'm going to either offer them drug 1 or drug 2. And I'm going to start off with these prior distributions over those drugs. So I'm going to start off not having any idea of the effect of drug 1, so it's got like this flat prior. These little diagrams here are like probability distributions over the mean, what I think the payoff will be for this particular drug. So I start off thinking that the probability density is flat. Like I don't know what the success probability of this drug is, so I'm just thinking it's kind of flat. There's a chance that it's going to have 0 probability, and there's a chance it's going to have 100% probability, and everything in between we're just going to say is kind of flat. But for the second one, we're going to assume it's probably around 50-50, but it could be anything still. And then we're going to proceed from there. Those are the priors. So now what happens is we could consider this whole look-ahead tree. We could say, well, I could pick the left arm. If I pick the left arm, I'll be in a situation where I would update my distributions in the following way. I would update my distributions to say, well, let's say I try drug 1 and it succeeds. Well, now I would start to skew this distribution towards success. I would start to think there's more probability that it's a good drug than a bad drug. But if it fails, I would skew that distribution in the opposite way. I'd skew it like this now to say there's some probability that this is more likely to be a failing drug. And so this is one way to just do a look ahead over this space. Once we're in this situation now, we can consider again, if this succeeded, I might look ahead again and say, well, now I'd be in an information state where I know this has happened so far. This is my statistic, my summary of everything that's happened so far. And I can look ahead again. And I could say, well, maybe I would try drug 1 again, and maybe it'll succeed and lead to this state, and maybe it'll fail and lead to this state. If it fails, I've now seen 1 success and 1 failure, so I think it's kind of around 50-50. That's that drug now. The right-hand one I've never tried, so I still think it looks like this, the drug 2. And then I might look ahead again and say, well, what happens if it succeeds or fails? And now we see we've got this whole MDP, like a tree search again. You can think of this as tree search, or you can think of it as an MDP. And if we solve for this MDP, we get the optimal trade-off between exploration and exploitation. Optimal, given our priors. Okay? So it's not a heuristic anymore. We're really saying, this is the best possible way to explore. We've looked ahead, we figured out all the consequences, how much I would learn if I was to take this decision, and we back that all up to get the answer. So, so to do this, we formulated the Bandit as an MDP, but now it's an infinite MDP. There's the number of information states is infinite and very large. But the MDP can nevertheless be solved by reinforcement learning methods. This is what we've spent the rest of the course on. So we can apply our favorite methods to this. If you use model-free reinforcement learning, you get a whole family of methods that can solve these things, maybe slowly with this original work here, but nevertheless can arrive at the right answer. And there's a very old, well-known theoretical framework for these bandit problems, which are called the Gittins indices. Gittins indices you can think of is the dynamic programming solution to this look-ahead tree problem here that we've looked at. Okay, so you can solve this thing by dynamic programming. We know the transition probabilities because we've created, we know what distribution we're using. We know that if this thing succeeds, we know how we would update our own distribution. So we know how our information states would transition. And this whole approach is called Bayes adaptive reinforcement learning. So it basically means you start off, okay, now let me clarify that. So we can work with information states, and there are many, many different ways to work with information states. If we characterize our information by a posterior distribution, then that's what's known as Bayes adaptive reinforcement learning. That you characterize, like in this drug example, what would it look like? It would look like characterizing everything we know about the problem by a posterior distribution over the payouts. So the Bayes adaptive idea is that in each state, you summarize all the information you know about that state by some distributions over how well your actions will perform. And then you solve for the MDP, where at each state you've got some distribution. So let's make that concrete. So in the Bernoulli case, what happens is that we start off with some beta prior at the beginning, at the root of this search tree. We start off with some beta prior. This is like our flat. We don't know how the drug's going to work, so we start off with maybe these things being like 0 counts, or maybe we have some other parameters for each action. And so for each action A, we're going to have some prior, like a beta prior, telling us how good we think that that particular arm is. And then every time an action is selected, we just update the posterior. We update this beta distribution. And the beta distribution has this really nice property that all you need to do is to count things. So what happens is if we see a reward of 0, all we do is we update our failure count. And we'll just adjust our posterior distribution. We increase our failure count by 1. And if we succeed, then we update our success count by 1. And this just changes our beta distribution a little bit. So the states of our information state MDP are, in this case, beta distributions. So we use the posterior of our of how good we think each of these drugs is as the state of an MDP, and we solve for that MDP. So just by writing this down, just by writing down the fact that if we succeed, then we'll increase our success count by 1, we've defined the transition dynamics of our MDP. And we solve for that MDP. Okay, so this is the Bayes adaptive approach. It's a way to, with a lot of computation, get the optimal solution to the exploration-exploitation dilemma. Okay, so there's just one more slide spelling this out, where we can start off with our prior distribution at the root here. So it's just telling us that for each of our actions, we've got some success counts and some failure counts, and you've got this kind of look-ahead tree that basically tells you how your distributions are changing, how your success counts are changing as you move through this tree. So each of these nodes, you can look at this afterwards. It's just showing the beta priors, and then the posterior after you see that change. Okay. So the exact solution to this problem can be computed by dynamic programming. It's known as the Gittins index. But it's also possible to find this in a more tractable way. For example, we use Monte Carlo tree search to come up with a very tractable approach to this very large information state space search. And that works very well in a lot of exploration-exploitation trade-off problems. So even though it might look like we've blown up our state space to something enormous, we can then use some of the planning methods that we know of that are very effective in large state spaces, like Monte Carlo tree search, to actually still find approximately a very good solution, and so approximate the best possible trade-off to the exploration-exploitation dilemma. Okay. So let's just summarize where we've got to so far. So we've been through a lot of ground already. We've covered an awful lot of things, but I think it's, these are really important ideas to understand. So we started off with we came in with our naive approaches. We can explore randomly. We can use epsilon greedy. We could use softmax exploration. Softmax exploration is where you just take your value function and you prefer better values but you still explore everything. You just exponentiate. You select things in proportion to how good the value is, basically. If you're in a continuous domain, you could use Gaussian noise. These are all examples of random exploration in the state action space, where you just, each time you're in a state, flip a coin, act randomly. You don't look at your uncertainty. These are myopic methods. They don't look ahead. They don't try and figure anything out. They just explore randomly. Then we had our optimism principle, optimism in the face of uncertainty. Estimate how much you know or don't know about your value, and use that to guide you towards things that not only that have the most potential to be good. So whenever you're not sure about something, try it more, because it might turn out to be a good idea. Can anyone think of a problem with that approach, by the way? What's a problem with the optimism in the face of uncertainty idea?
If there's a lot of possible options, then you might end up spending a lot of time doing suboptimal things.
Right. So if you're in some infinite action space, you just keep exploring and exploring and exploring, and you never end up exploiting, because there's always more uncertainty to explore. Another problem is if you've got some real robot, and there's a cost to actually you want to avoid catastrophes. What happens if you want to avoid catastrophes? This doesn't give you safe exploration. If you actually talk to some people in industry, they sometimes do the opposite of these ideas. They don't want to systematically explore the state space. They prefer to explore around the things that they know are safe, and never go too far away from things that they know are safe. You don't want to crash your helicopter. You want to kind of do things which you're pretty sure are going to be safe. Anyway, it's a very fundamental principle that really, really helps in cases where you really want to make sure that you do explore the whole state space. Optimistic initialization, the simplest form, where you just initialize your values high and assume the best about something until proven otherwise, until you suppress its value back down to its realistic value. The UCB approach, where we basically use some upper confidence bound on the value to guide our exploration. And Thompson sampling, where we do probability matching, where we basically pick things in proportion to their chance of being the best thing. And then finally, we have the information state space idea, the kind of theoretically optimal approach, where you kind of do look ahead in this whole space of all the decisions you might make, how they affect how much you know about the problem, and then look ahead and figure out the best path through this information state space so as to really figure out which of those leads you to the best possible solution. Okay, so that's sort of the map of where the methods we've seen so far. I can take some questions, and what I just wanted to do is to explain very briefly how this maps into MDPs and problems where there's state. So there's no questions. Okay, good. One question.
Very quick, on the information state space, is your reward signal unchanged, or are you adapting the reward signal to take into account the information, or is it just updating your state definition?
The reward function is unchanged. We're not changing the reward function in the information state space. So we're keeping the reward. The reward in our MDP is the same as the reward function in our Bandit. All we're doing is we're adapting our value function to take account of the fact that we're not just stopping after one step. We're imagining what happens not just after this one pull, but after many pulls. What's the value of those rewards over time, taking account of how much information I acquire along the way. So if I acquire information, it might lead to more rewards in the long term. And there might be a budget of how many samples you're able to test, and this approach can really factor in your information state space MDP might have a transition function that stops after a horizon of 10. And now you can really optimize for that horizon and just do the right thing. Okay, so what I'm going to do is I'm going to explain the contextual bandit problem, but I'm not going to explain the solution methods. I'll leave those for further reading in the slides. This will then be non-examinable. So, and then I'm going to move on to very briefly just touch on how these ideas extend to MDPs. So a contextual bandit basically takes our multi-arm bandit formulation and it adds in one more ingredient. So what we're doing is we're putting states back into the picture. So we still have this idea that we pull an arm, and as a result of that arm, we're going to get some payoff. So we've got some action space, which is our arms. We've got some payoff, which is the rewards. And the canonical example now is going to be like banner ad placement on the internet. So a user comes in, and we need to show them some advert, and we want to maximize the probability they actually click on that advert. assume that we're some cynical company that's trying to just maximize click-through, or alternatively help the user experience what they want to find, depending on who you talk to. And now we basically want to figure out how to do this. And the key thing is that we've got some context. We don't just come into this blindly. We don't just show the same things regardless of who comes in. We track some statistics. We're told something about the user, like maybe we're told, what continent they're on, or maybe we're told something about the history of what they clicked on in the past, or some other statistics about that user. And so we want to shape the adverts that we show to users depending on what kind of user they are. And so that state then becomes this S, some context information. So we're now shown a state, we're given a state, and we need to pick an action, and then we get some reward. And then you're shown another user, you're shown some state, you get to pick an action, you get a reward. Do they click or not? And so there's state now informing what you do. And so we basically extend our reward function to depend on the state as well as the action. And now at every step, we're basically picking this action, and we're again trying to maximize the cumulative reward that we get over many, many steps. And this is the contextual bandit problem. And there's, I think you can just read about this. And there's an example that's taken from Yahoo. This is the front page news problem, where they use this contextual bandits to select what news article to recommend to an individual based on the statistics they've seen about that individual. And you can just see from these examples what happens when you use some very simple contextual bandit algorithms. They get this very, very nice improvements in probability. They're able to actually pick news articles that are very appropriate to people and make them much more likely to click on them by using this kind of contextual bandit approach. Again, using an upper confidence type idea. So in the lecture slides, you'll find the upper confidence bound approach extended to contexts using linear function approximation. Okay, I don't expect you to understand that right now, but feel free to have a look at that. Very briefly, how can we take the ideas we've seen so far and extend them to the full case that we care about if we're really building an agent? Right? We want to do reinforcement learning. We want to drop down our agent into Atari, or our robot into the real world, or our helicopter and throw it out there. We want to understand how to trade off exploration and exploitation so as to find the best solution to whatever problem we're addressing, whilst getting as much reward as possible along the way. So this is just to say that all of the ideas that we've seen in previous sections extend to the MDP case, every one. So you can take upper confidence bounds for MDPs instead of for bandits. So what would that look like? Well, what we would do is we would take our Q value, our action value. We say I'm in some state now, and I'm considering all of these actions. And if I know some kind of uncertainty of these Q values, I might say, well, let's add on some bonus which encourages me to explore the actions that I've tried least, or encourages me to explore the actions that I'm most uncertain about. It's the optimism in the face of uncertainty principle extended to MDPs. And so if I know that idea, that gives me a way to pick amongst actions, so I always pick the one that I'm most unsure about. And so there's the first idea of which did this was an interval estimation method, where you basically just have some method that says my Q values, I'm pretty sure they're between 10 and 20, and then we just pick the top end of that interval as the value that we use. You can also use the more sophisticated methods that we saw with Huffling, inequalities, whatever. One thing I want to stress about this is that this idea is not quite perfect in MDPs, because this ignores a very important fact, which is it ignores the fact that when we're in an MDP, and we're just evaluating our current policy, that policy is likely to improve as we start to, if we're doing control in the MDP, we're going to start improving our policy, and the Q values are actually going to get better and better and better and better. So the uncertainty correctly should take account not just of how uncertain our Monte Carlo estimate is so far of the current Q value, it also needs to take account of how much more our policy could improve. So our Q values could be wrong in two ways. They could be wrong because I haven't estimated my current policy, haven't evaluated my current policy well, or they could be wrong because there's a lot of improvements I can still make. So correctly, we need to take account of both of those, and that's hard to do. One approach I just want to mention, which is an optimism in the face of uncertainty principle, which is very popular for MDPs, is the following idea. It says, let's be model-based. Let's construct a model of the MDP, but then let's imagine that for any state that I'm not sure about, any state that I don't really know what the value is, any state that I'm not really sure what the reward function is for this state, let's imagine that that state is like heaven. So anything that you don't know about yet and you haven't fully figured out, pretend it's heaven. Now, what you do is you run your favorite planning algorithm. What's it going to do? Your planning algorithm is going to figure out how to get to each of these states that you don't know about. It thinks that there's some state that you haven't visited yet, and it thinks that state is heaven. So it figures out how to take you to that state. You visit that state. You start to figure out, actually, that state wasn't heaven. It was actually pretty crappy. And then you don't explore that state again. And next time you solve for you update your model now to reduce the value of that particular state. And then you solve again, and it will encourage you to the next heavenly state until you've suppressed all of the rewards down to realistic values. So it gives you very systematic exploration. So the best known example of that is the Softmax algorithm, or E-cubed is another variant of these ideas. Many variants there. Finally, the information state space idea also applies to MDPs. So this is the correct approach. This is the idea where we can systematically say how much information should I gather and what's the value of that information. We can do that with MDPs as well. So in this case, what we do is we start off with our original state space, and we augment that state space to combine it with information. So we basically say we're going to invent a much bigger, more complicated MDP in which our new state of those MDPs is the state that I was in my real MDP. So this is like where the robot is in the real world. And also, we're going to augment that state by the information that is gathered so far. So the state of my augmented MDP is something like, I'm in a position that's here, and I've also visited all of these things over there. So you kind of remember what you visited so far, that's the I, and you also know where you are. And you make that your augmented state, and then you solve for the augmented state, this augmented information state MDP. You solve for that using whatever method you choose. For example, we can again use Monte Carlo tree search. That's a very effective approach that we tried. And you can get really, if you can solve this thing, it blows up to a very, very large MDP. But if you can approximate the solution to this MDP, you start to get the optimal trade-off between exploration and exploitation. So this actually has proven quite effective, at least in some cases of moderate complexity. Hasn't been scaled up to really challenging MDPs yet. Okay, so we've looked through these kind of progressively more complicated approaches to exploration and exploitation, starting with random exploration, bringing in this principle of optimism in the face of uncertainty, and finally looking at the most systematic case where we use the information state to guide the optimal solution to these exploration exploitation dilemma. We've also looked at progressively more complicated settings. We started with the multi-armed bandit, we progressed through contextual bandits very briefly, and then touched on MDPs. And so this space really tells you about what are the solution methods and problem types that you can combine together so as to get a handle on the exploration problem in reinforcement learning. Okay, thanks everyone. So I just want to important notice, so the final lecture is at a non-standard time. So I posted to the mailing list and it's up on my website, but the final lecture will be taking place next Wednesday, not on Thursday. I believe it's at 10 a.m. In Roberts G06. Check the website, make sure I'm telling the truth. But I'll post again just to confirm that's the case, but it's not here. Don't come here. It will be closed next Thursday. That's a UCL holiday anyway. And again, just to stress that that's going to be non-examinable material, so I know it's outside official class times. You won't find yourself doing worse than the exam if you can't make it, but it should be really fun. We're just covering games, it's a case study. There'll be 0 equations, very few equations. Okay, thanks everyone.